So let me try this one again. We're dealing with coordinates in R3. We have rectangular, cylindrical, and spherical coordinates. And since this is Calc 3, we need to be able to write triple integrals using each of those different coordinate systems. The issue that we have in cylindrical and spherical coordinates is that one or two of our variables represents an angle. So if I have d theta or d phi, that is not a length, so it doesn't contribute to the dv, which is a little piece of volume. I want the dv to represent some volume. And d theta and d phi are not volume, or are not lengths, so they don't contribute to volume. We're going to do the same thing that we did in double integrals in polar coordinates. D theta becomes a length when we use the arc length and say, how far is this d theta from the origin? Then it becomes a little arc length, and even though things are a little bit rounded, we say it's close enough because d theta is going to be really small. So in rectangular coordinates, dx, dy, dz is all dv. Those are all three lengths. Length times length times length, that gives us a volume. No problem there. In cylindrical coordinates are just polar coordinates with a z-axis. In cylindrical coordinates, we have the variable r, and that's how we turn d theta into a length, so we just use that. So in cylindrical coordinates, if we write our function in r, theta, and z, dr is a length, but d theta is not a length. We need to multiply by r to turn d theta into a length. So r, dr, d theta, dz, that is what we need for dv. Now, when we go to integrate, r gets integrated along with the function f, but the r, dr, d theta, dz is our dv, our little piece of volume. So r, dr, d theta, dz, that's what all the pieces that we need to make a dv, a little chunk of volume in the solid W. In this one, r turns d theta into length. In spherical coordinates, we're going to need two of these factors that turn angles into length. We're going to need two factors that turn the angle into a length. The easier one is phi. If I include an extra factor of rho, that's how far. So if we put a d phi in here, that d phi is rho units away from the origin. So for the dv in spherical coordinates, rho makes d phi length. In spherical coordinates, rho will make d phi into a length. Because our d rho will be up here, or our d phi will be up here, rho units away from the origin. In the case of theta, we had r turning theta into a length. Because here's our d theta up here. It's r units away from the origin in the xy plane. The problem that we have here in spherical coordinates is that there is no r. So r makes d theta length. The problem we have here is that there is no r. I've got rho, theta, and phi. So fortunately for our heroes, right at the top of the page, I wrote down the relationship between cylindrical and spherical coordinates. R is equal to rho times the sine of phi. So instead of r, you can replace that with rho times sine of phi. D rho on its own is a length. So what we need is rho to turn d phi into a length. We also need rho times the sine of phi to turn d theta into a length. Rho sine phi is r, but we don't have r. We have to write it in terms of spherical coordinates. So I need another factor of rho and the sine of phi. Then I can have my d rho, d theta, and d phi. Rho turns d phi into a length. Rho sine phi turns d theta into a length. And d rho is already a length. So here are all the pieces that we need for dv in spherical coordinates. If we went, so the rho squared sine phi is part of dv, but when it comes to the integration of things, that gets integrated along with the function f. Let's suppose that we wanted to write a triple integral for the volume of a sphere with a radius of 3. We integrate the function 1 for the size of the set over which we are integrating. The advantage of using spherical coordinates is that our shape is a sphere. We are trying to describe a round thing. We're going to use round coordinates to do it. So a sphere in spherical coordinates will just be a bunch of intervals. We're going to integrate the function 1, but I still need rho squared sine of phi from part of the dv. Rho squared sine phi. Then I need a d rho, d theta, and a d phi. Since we know that a sphere is just going to be 3 intervals, we can do this in whatever order we want. So for a whole sphere of radius 3, well, let's just use the order we did up here. What does rho go between? Start at the center and go out to 3. So we'll take rho from 0 to 3, all over the place. Let's put in theta. We want to go all the way around. So what values of theta do we need? 0 to 2 pi. So theta will go from 0 to 2 pi. And phi, 0 to pi. Because that'll give us the top and the bottom. 0 to pi over 2 is the top half of the circle, and pi over 2 to pi is the bottom half of the circle. These are just three constants, so we can actually integrate in whatever order we want. This is the first one that occurred to us, so this is the one that we could go with. Now we know we're going to get 4/3 times pi times 3 squared, 3 cubed, 4/3 times pi times 3 cubed, because we remember the formula for the volume of a sphere. So with that in mind, we got to figure out where the 4/3 is going to come from and where the pi is going to come from. So here we go. So we start off, we integrate d rho. And so I've got a rho squared. So the integral with respect to rho will be a 1/3 rho cubed. And then we still have sine of phi. And then we have to evaluate from 0 to 3. Here's where we see that 3 cubed showing up. Here's also where we see the 1/3 showing up. It's like I'm trying to hide it down here at the bottom. Only people in the front row get to see what's going on. Back row, it's like, oh, see like that? Oh, but now you can. So the 3 goes in for rho, and that gives me the 3 cubed that we're going to want to see. So it's going to be a 1/3 times 3 cubed. And then we still have the sine of phi. When we plug in 0, we get 0, so we're not worried about that. We still need the integral d theta, and we still need the integral d phi. Theta is going to go from 0 to 2 pi. And phi is going to go from 0 to pi because we want the whole sphere. Now we can integrate d theta. This function is currently constant with respect to theta. So when we integrate with respect to theta, we just get the 1/3 and 3 cubed. Theta shows up. Nope. Because we're trying to see where all the elements come from in 4/3 pi r cubed. We see the r cubed show up. I want to leave it there. The thirds part is still there. We got to find out where the 4 and the pi are going to be coming from. So this we integrate from 0 to 2 pi. So when we plug in 2 pi, we're going to have a 2 pi over 3. I'll write it in the way that I write all my. So there's the 2/3. Then when we plug in 0, we get 0. So don't worry about that. But we still need to integrate d phi. Now we can see where the other 2 is going to come from. Because we're going to drop in a cosine at pi and 0. And there's going to be negative cosine. And we're going to have a pi and a 0. So now we're integrating d phi. And we evaluate from 0 to pi. At this point, plugging in the 0 is not going to just result in 0. So I'm going to have the two terms. I'm going to plug in pi. Cosine of pi is -1, takes care of the negative. Cosine of 0 is 1. Sorry, cosine of 0 is 1. In this case, the cosine of pi is -1. That cancels out the negative. Negative from the definite integral cancels out the negative from the antiderivative, leading to a plus. And here's where we get our 2/3, our 4/3. So 2/3 and 2/3 is 4/3. Pi times r cubed. Questions? Integrating the function 1 gives you the size of the set over which you are integrating. It's like the integral from a to b of f prime of 1 dx is b minus a. That's the length of the integral. The integral of 1 dA in a double integral will give you the area of the region. The integral of 1 over w dv will give you the volume over which you are integrating. One of the things that we mentioned previously is that for a volume problem, we like to use as a model a variable density. If our density is constant, all we have to do is take the volume and multiply by the constant density. And if we drop the constant density in here of, let's say, 2 mass units per volume units, that would just take this whole thing and multiply by 2. The volume multiplied by the density, just like we expected. Now, if we had to, for example, if we had a shape where the density varied differently, let's say the density varied with z, then we would have to write the density in spherical coordinates, or we would have to write the sphere, the integral part of the sphere, in coordinates with z, in cylindrical or rectangular coordinates. So depending on what kind of function we get that we're trying to integrate, depending on how that function varies, that will determine the best coordinates to use. Do I want to make the function I'm given, say variable density, in spherical coordinates, or do I want to rewrite the sphere in cylindrical or rectangular coordinates? Any questions? How's everybody okay? Everybody looks stunned. This is what it looks like on a Friday in the afternoon. No one has any questions. No one will have questions at this point, because you're just like, oh, I just need to get through until 1 o'clock so I can leave. Then I will worry about it on Sunday night. I'll have like 48 hours where I can just like not care about math. And I don't have to listen to Leach talk. I mean, the feeling's being solid. All right, everybody gets it now. I can be like, a fundamental theorem of finitely generated abelian groups. Any questions? You'd be like, oh, nope. What's this fundamental theorem business? What's a finitely generated abelian group? Don't care. I'll worry about it on Sunday. It's Friday. Friday.
This
Any questions? Comments? Snide remarks? Is everybody okay? We're like 9 weeks in, so we've passed halfway. Yes, it's like this, that the 095, that's week 9, day 5. Eight weeks to go. You have to go through week 17, day 5. After that, we have a final exam, and then you all are done. Your calculus journey will come to a close for now, if you pass.
Welcome.
Any questions? Comments? Thoughts? Well, I am making my life easy. I'm making my life easy by finding the volume of a sphere in spherical coordinates. Now, if we wanted to make our life spicy, then what we could do is take this sphere and like truncate it in with some flat plane. If you think back to Calc 2, I'm not sure about the Calc 2 class that you took, but the one that took place in my mind, where one of the things that we did was take a spherical container and only partially fill it, right? So we have to figure out where we integrate. So in the sphere from negative, we would integrate the whole thing from -3 to 3, because we were using just one variable, because that's the limitation in single variable calculus. You integrate from -3 to 3, but if I say truncate the top 2 units, we integrate from -3 up to 1, right? Which I say, and I phrase it by saying the depth of the water in the thing is 4. How much water is it? And you have to know to integrate from -3 up to 1, or do a substitution so that you can integrate from 0 to 4. So one of the things that we would want to think about, what if I take this sphere of radius 3 and I truncate 2 units off the top? So what if we truncate 2 units off the top? I would have to cut off a flat plane where z is equal to 1. That'll take the top 2 units off. Out of truncate where z is equal to 1. The problem is z is not one of our coordinates available in spherical coordinates. We might want to rewrite this integral in cylindrical coordinates because it has that z. And I could just integrate from the bottom of the sphere, -3, to the top of the sphere, 1. But that would mess up all the stuff in the middle. Or we could try to describe that plane where z is equal to 1 in spherical coordinates and figure out what other messes we create when we do that. So we can write z equals rho times the cosine of phi. So rho cosine phi is equal to 3. So rho is equal to 3 secant of phi. But then I wouldn't be able to use that one, let's say, at the end. So I'd have to figure out what values of what values of phi we're integrating. If I cut off the top, I still want to go all the way around. So 0 to 2 pi, theta still works. But we're not doing phi all the way from pi down to 0. Or sorry, from 0 down to pi. Because we're not going all the way up at the top. We have to figure out what angle that phi is going to be at with a z of 1. Any questions? Notice that I keep bouncing back and forth between the spherical coordinates, and I keep describing that plane the easiest way possible with z equals 1. This is because we have to know all these different coordinates. We have to be fluent in all 3 different languages. That's shocking for Americans. It's like, well, now we just speak English here. Like, well, but it's very limiting. So we have to know all the different coordinates. Any questions? Comments? Snide remark. This is what I wanted to talk about yesterday, but then I got distracted. What did I talk about yesterday?
The lottery.
Oh, that's right. Numbers and the lottery. Always, you're lucky I didn't start talking about like starting a retirement account. If you haven't started a retirement account, you need to get on that. I don't know. Go find an index fund, put money in it. Any questions? Comments? Slide it on. All right. That's going to do it for today. What I want you to think about is how you would describe things. Think about an object. So what would be the best coordinates for that? This is this thing that I'm holding up. You can't see it there. There you can see it at home. I would use cylindrical coordinates for this because this is a cylinder. Like even if I said the cylinder is sitting this way, that's fine. We could just take our z-axis and turn it sideways, and then the z-axis can go this way. That's fine. It's a cylinder. That's the shape. That's the graph paper I want to use to describe this thing. I don't know. There's different cylinders on top here. That could be messy, but doesn't matter. Cylindrical coordinates. If I want to describe this thing, probably rectangular coordinates, it is pretty much a rectangle. That's kind of also a flat thing. But if I want to describe this thing, this is the case that I carry my camera around in. It's rectangular coordinates. So I want you to see how and think about how you would describe objects that you come across. Any questions? Start seeing the world in rectangular, cylindrical, and spherical coordinates. That's going to do it for today. That's going to do it for this week. I'll see y'all next week. Everybody have a good weekend. And thanks for playing.
Bye, Professor. Have a good weekend.
Thank you.
Bye.